like that. Those people who said integration was difficult, they were full of garbage. Like I remember thinking that coming out of Calc 1. And then, boy, was I wrong. Now, no, it's just the tip of the iceberg. There's more to it, right? So what happens is the concepts that are associated with anti-differentiation, taking antiderivatives, integration, all meaning the same thing generally. They're more like exercises in case studies, because what happens is under certain circumstances you'll use one technique, and in other circumstances you'll use another technique, and before you know it, you have about 20 disjointed techniques for finding antiderivatives, which in and of themselves aren't difficult. Like if you have basic sense of algebra and you know your derivative rules, then that part won't be fine. Won't be fine. Geez, that's the opposite of what I'm trying to say. That part won't be the problem. The part that will be the problem is distinguishing when to use one technique over another, right? So that requires fluency. In order to develop fluency with anti-differentiation, you need to know derivative rules like the back of your hand, right? So on this page here, we're going to talk about finding antiderivatives, and in some cases, some pretty complicated looking expressions, but they're all rooted in our knowledge of derivatives. If you know how to take a derivative and you know the rules for the weird cases, then anti-differentiation becomes that much easier, right? But before we get into that, we got to talk about notation, because you see that funky S, and if you don't have any experience with integration, then that already is throwing you for a loop, right? So antiderivative, anti-differentiation means working backwards, in the sense that we've been taking derivatives all this time. Now we're going to go the other way. We're going to undo the process of taking a derivative, right? The general form of an antiderivative is given as capital F of X plus C, right? And so what that would mean is that the derivative with respect to X of some function capital F of X plus C would be equal to lowercase f of X. The C goes away because the C is constant, all right? So I'm just going to reduce this inside a little bit, or as I say, schmidge it down. All right. Now, if I then take the derivative of this f of X, right, which was the result of taking the derivative of the capital F of X, all right? If I take the derivative of the f of X that gives us a result of f prime of X, all right? This is where we've been living, all right? But what we're going to do now is work with this, right? And so it gives us sort of a hierarchy where you have your function of X kind of living in like the middle realm, if you will, right? So you got the underworld, the heavens, and then you have ordinary f of X right in the middle, you know? So if you go backwards from f of X, you get to the antiderivative. If you go forwards from the f of X, you get the derivative. All right, so the hierarchy is your equilibrium is f of X. Swing in one direction, you go to the antiderivative. Swing in the other direction, you go to the derivative. All right. But like I said, we're going to be working with this. And so if I take this and just kind of jot it down here, and what I'm about to write is really rehashed in the notes, all in the type notes. It's just, I always found that when I left people to their own devices to interpret the stuff that I just typed, it doesn't always play out the way I want. So I'm just going to rewrite it. We have d dx is equal to f of x plus c. That's equal to, like I said, f of x. All right. So this is a differential equation because it involves a derivative. All right. And you can see it's noted down here. All right. But what I can do when we talked about differentials, this goes back to linearization, Newton's method, and differentials. I can multiply both sides by a dx. So I would have d f of x, capital of f of x plus c, is equal to f of x dx. All right. So this part is kind of strange in that in my next step, I would need to do something to kind of like undo what's going on here, right? So if I wanted to release the capital F of x plus c from the captivity that is the d, that means that it's a derivative. It's just looking at the instantaneous change in the y part of it, the capital F of x. The only way to do that would be to reverse derivative this whole thing, which we call an antiderivative. The symbol for that is this funky kind of S. It's an operation that can be applied to both sides of an equation. It's like a square root or a power, or just simply multiplying both sides by a number, right? But in the case of, like, let's say if you have one side of an equation raised to the second power and you want to get rid of that, you take the square root. That's because the power of 2 and the square root will cancel each other. That's what's happening over here. These two cancel each other out, and we end up with capital F of x plus c is equal to really just the antiderivative of this, right? So the antiderivative of f of x dx, right? But there's really not much more we could do at this point without knowing what the f of x is, right? But what this is really telling us is that I'm going to get an answer. If I were ever to find out the answer to this, as in I know what f of x is, and I could actually do the work to find the antiderivative, that would lead me to an answer that would be in this form. So that's a lot when it comes to the notation. But what people will say is, all right, just tell us the rules and that'll be great. But the thing is, the rules are one thing. Understanding what the notation is talking about makes all the difference. Yeah, and it takes a while for people to come to grips with that. But and there's been different kind of waves in terms of like schools of thought involving education. And they're like, all right, as long as they get the gist, it's good. To now, it's like, listen, if you don't understand the notation, then what are you even doing? Right? The reality is somewhere in between, but that's what it all comes down to, right? So what that all was, and that whole explanation that I just kind of squeezed into that corner, it's elucidated, if you will, over here. All of this stuff really gets at that. It's just more itemized and typed, right? So that gives you this expression. So I'll walk you through how to properly frame an antiderivative in terms of an actual function in a few minutes. But for now, we just want to focus on some basic rules. All right. So knowing what the derivatives are of certain functions, like from the beginning, middle of the course, that's going to pay dividends now. Right. And some of them I'll have to give you, because we haven't had we haven't learned the skills necessary to figure them out on the derivative end. But that most of them we should be able to come up with. Like, for example, the antiderivative of 0, right? So I'm looking for some number or some function whose derivative is equal to 0. Now, yeah, I mean, you do a little guess and check. You'd be like, all right, f of x equals x, right? There's a function. And you're like, well, what's that derivative? F prime of x. A 1. All right, well, okay, so that's no help. Although that will be helpful in a minute. But if I have like 2x, for example, that's a 2. If I have a 3x, that's a 3. If I have a 4x, that's a 4. That's kind of a nice piece of information to know. So if I have a linear equation like 4x plus 5, its derivative is just going to be the slope, right? So that's useful. But I'm thinking about what function would have a derivative that's just equal to 0, right? So that's really what this is asking for, because this number here, let me make it a little cleaner. This function, everything between the s, the funky s, and the dx, known as an integrand, like radicand is the thing under a radical, integrand is the thing in the integral, right? That's the thing that is the result of a derivative, right? So if the structure is that capital F of x plus c is equal to the antiderivative of f of x dx, then whatever is between the funky s and the dx, that's going to be the function. That's the thing that I'm looking to evaluate, right? So that's, I have to find the antiderivative of that, but I can also look at it the other way and say, if I find the derivative of this, then it must be equal to that, right? So the derivative, again, of the f of x, and we could just focus on the f of x because we know the c is going to 0, is going to be equal to f lowercase f of x, all right? So I'm thinking about it from the reverse standpoint, not like invent some calculus right now in your head of like, what's the antiderivative? It's like, dude, we're just learning about this now. No, you think, okay, what function has its derivative equal to 0? Well, it would be a constant function. So let's say I started typing in the 4, like I thought, for example, it was 4x plus blah, blah, blah. I only got as far as the 4, and I'm like, oh, wait, whoa, 0. Look at that. My derivative's equal to 0. I'm on to something. What about a 5? Still a 0. What about a 9? What about a -5? What about a -1? Negative 1, that's fun. -1. How about a negative pi? That works. That's a 0. How about a negative e? Still 0. How about negative natural log of 2? No variable in it, so it's still constant. Any constant is going to have a derivative equal to 0. So I would just say C for constant, right? And I kind of throw that up here, but if we let C be some constant, then the antiderivative of 0 is just going to be some constant. All right. So then they're saying find the antiderivative of k dx. So I'm thinking, now k is another type of constant. So there's a constant that comes through the process of integration, and then there's any constant that would be in existence in some sort of formula. Like, for example, if you have an exponential growth formula, you have the rate of growth. That would be some constant. Spring constant, gravitational constant. These are all constants that are known quantities. So this is some known quantity It's just I don't know it, right? So like the gravitational constant on Saturn, right? I don't know what it is, but I know it's a known value. So I would call that K, right? So what I'm looking for is some value, some expression that has a derivative equal to K, right? So, I mean, I could try putting in a K, add a slider for it. If I do a K, K has a sliding value that is constant. Derivative of a constant is equal to 0, right? So that's no help, right? So the derivative of K would not be equal to K, but the derivative of Kx, see how K and its derivative are the same thing, that actually checks out. So what we're looking at is kind of the formation of something known as the reverse power rule, because no matter where I put the K value here, let's say negative 1.6, negative 1.4, I'd have negative 1.4x as my function. Its derivative would just be negative 1.4. So whatever that K value is, its antiderivative is going to be K times X. But there could also be some constant added on at the end. Let's say Kx plus 2. It's still negative 1.4. That 2 didn't factor into the derivative in any way, nor did this 3, or this 9, or a pi, or an e. It doesn't matter what that constant is added on at the end. So anytime you take an antiderivative, there's an assumed constant of integration added on at the end. All right, but let me just show you a quick other way to do this. Let's assume, again, f of x is equal to k. If k is a constant, we could still think of it as a constant multiple of the variable x. It's just that x would be raised to the 0th power. All right, kx to the 0th power is the same thing as k. All right, anytime you're unsure of something, just pop it in. All right, kx to the 0th power. All right, and then, you know, y equals, if you weren't sure after that, y equals k. You'll see that red and black are going to the same location. No matter where I slide my slider, they're going together, the same function. All right. So with the power rule for derivatives, I would multiply my power by the coefficient and then reduce the power by 1. Multiply power by coefficient, reduce the power by 1. So what I'm going to do here is I'm going to, in order to find the antiderivative, is I'm going to increase the power by 1. I'm going to do everything in reverse. So multiply power by coefficient, reduce the power by 1. So my last step there was reduce the power by 1, so increase the power by 1. My first step originally was multiply power by coefficient. That should be my last step now. Instead of multiply power by coefficient, divide coefficient by power. So k over 1, k, x to the 0 plus 1, x to the first, just kx. All right. So that's it's exactly the reverse of the power rule. You're taking what you did with the power rule and you're doing it backwards. Every aspect of it backwards. It's like you're reading the steps word for word in the reverse order. All right. So that actually helps us with something like this one here. I'll come back to the kf of x one. That one, I have an x to the n. Increase my power by 1, divide by the new power, right? But divide what by the new power? The coefficient. Well, the coefficient was what? Well, it was an understood 1. So let me just tuck that in there. Take that 1, divide it by that new power, which is n plus 1. But then I'm going to tack on a plus c at the end because there always could be a constant of integration. If I take the derivative of a constant, I should get 0 as a result. So just remember, the way to check this is to just take the derivative of the thing that you think is the antiderivative. Okay. Another way to do it, I mean, Desmos is, it's great with the sliders, but if you have an actual function, not in terms of like an unknown n as your exponent, like let's say it's just the antiderivative of x squared dx. I mean, you could try to put it in because there is an integral function. So function under miscellaneous, but the thing is it's definite. Now there are ways to come up with a definite integral that'll actually map out an entire function, but we're not there yet, which is why I'm not leading with that. If there was a way to just type it in and it would tell you the answer, I would have already told you that, right? But what you would do is you'd actually leave your bounds variable, but I haven't even talked to you about bounds yet. So, but there is an integral function and we'll come back to that. But for now, what I would say is take the thing that you think is your answer, put that in as a function, right? So f of x is equal to 1 divided by n plus 1 times x to the n plus 1 plus some constant c. I mean, you got sliders galore here, but in case you wanted to know, this is the different possible variations of what the function could look like. All right, this is what we think the antiderivative function would look like. All right. So then I would just take the derivative of that, f prime of x. All right, that should match my integrand. Right, so I would actually turn off this function, the original one I put in. I don't even want to look at that anymore. This, what I have in blue, should be equivalent to y equals x to the n. If it's not, then either I found the one instance where Desmos doesn't work, or I made a mistake. In this case, everything's coming up roses, right? So what I suspected was the antiderivative is equivalent to the integrand. That's great news. And for all values of c, because no matter where I put the c value, it's not manipulating the f of x at all. All right. So that's great news. Right. Now, going back to the previous one, that's actually related to what we've referred to as a constant multiple rule for derivatives. This is really just a constant multiple rule for antiderivatives, right? So that k doesn't have an x in it. It's a factor that doesn't have an x in it. So it actually doesn't even need to be in the integral, right? And it didn't need to be in the integral in the previous one, but we still would have had a constant in there anyway if we factored it out, because you factor out a k, it would have left you with a 1. But here, if you factor out a k from the integral, it leaves you with a lowercase f of x dx. All right. Now, that may seem familiar, although I don't expect you to have instant recall on something I just taught you like 5 minutes ago, but it is written right here. The antiderivative of f of x, lowercase f of x dx, is equivalent to capital F of x plus c. So through direct substitution, I can replace this. So I'd keep the k. This would be equivalent to capital F of x plus c. And so I could leave it like that, or I could distribute through the k. All right. So it would be k capital F of x plus, now I could write it as kc, but the constant of integration c is something that we call an absorbing constant. It's actually a constant that is the black hole of constants, as in it sucks in all the other constants, right? It absorbs them all to be part of its collective consciousness, right? So really what it's saying is, if you multiply a constant, any constant, whether it's just a simple number 2 or a constant k or a gravitational constant g, whatever it happens to be, it's going to get absorbed by the constant of integration, right? And become just a c, right? And the reason why that's a thing is because I know that this is the antiderivative of lowercase f of x, which means if I take the derivative of this, I should get this. Right, whether I write it as kc or just c, it's going away anyway in the derivative process, because the derivative of a constant is equal to 0. So it becomes irrelevant. Right? So we just consolidate it all and write it as just one single constant c. All right. Now 1 over x, that could be written as x to the negative first dx. Now, if you try it, I'll spare you the details here. But if you were to, let me just resize a little bit. If you were to write this or try to find its antiderivative using the reverse of the power rule, increase the exponent by 1, divide by the new exponent, you'd be dividing by 0. All right. So that's no good, because you get something that's undefined. But we do know, and we've experienced this, there is a function out there whose derivative is 1 over x. Because again, ultimately, what our goal is to find the function whose derivative is the function that's trapped between the funky s and the dx. Right? So I'm looking for the function whose derivative is 1 over x. Right? And this is what I was saying before, or what I meant before when I was saying that your knowledge of derivatives will help you immensely in finding antiderivatives. It's one thing to be able to look things up, it's another thing to actually know it. So the derivative of the natural log of x is equal to 1 over x. Right? So this stuff becomes irrelevant, except to remind yourself that if you try this process, the reverse of the power rule, or even if you want to write it this way, it's not going to work. All right. So let me show you in Desmos. Let's say, I have my reverse power rule written in here. Right. You have your f of x is equal to the 1 over n x to the n plus 1 plus c. So I'd be looking for some function that when I reduce the power by 1, the new power becomes -1, right? So if I reduce an n value by 1, my new power would be n minus 1. But in order to get a result that is equal to a -1, the original power would have had to be a power of 0. All right. So x to the 0th power, x to the 0th power disappears. It cancels away. It's constant. The derivative of constant we know is equal to 0. We have a contradiction. Right. So if I were to say the antiderivative of 1 over, well, in this case, 1 over x, I would be increasing the exponent by 1. That would get me to an x to the 0th, but then I divide by that new power. I'm going to get 0 in the bottom of the fraction. Right? It makes it undefined. Right? So, I mean, I could try to put undefined in here. I'd have to slide my slider to a -1. I mean, I'm not getting anything. Hold on. I'm not getting anything for the f of x. Doesn't show up on the graph. I mean, my derivative, not much better. I mean, there's nothing present. I mean, the c is irrelevant, but it's undefined. It doesn't work, right? But if you know that the derivative of the natural log of x is equal to 1 over x, just by studying, so you did your part, you worked hard, and now you're waiting for it to pay dividends. It's like, all right, here we go. What's my answer? Well, the derivative of natural log of x plus c is equal to this funky graph. Okay. Well, that's good. But y equals 1 over x is this graph. Got a little extra. Same graph on the right side, but we got a little extra stuff on the left that we don't want. All right. So what I would say here is that the antiderivative of 1 over x dx is the natural log of x plus c, but that only applies for the f of x values that are greater than 0. All right. So for f of x on the interval of 0 to infinity, not including the 0, because that would have made the original function undefined. All right. So I could turn this off, I could turn this back on and restrict its domain to be only values of x greater than 0. And now my antiderivative matches up with the correct antiderivative. All right. Because you have a domain restriction when you deal with a natural log, and that becomes an issue. Now, again, prior knowledge. We know the derivative of e to the x is e to the x. So the antiderivative of e to the x is e to the x plus c. All right. That one's nice and easy. The derivative, and I'll just kind of chuck this off on the side, the derivative with respect to x of a to the x power is a to the x times the natural log of a. Well, what this is saying is that I'm starting with this, just this piece, and I'm looking to find the antiderivative. So the antiderivative of a to the x is not just going to be a to the x. That'll be part of it. But I have to reverse engineer this. Well, to find the derivative, I would have an a to the x multiplied by ln of a. So perhaps my antiderivative would be a to the x divided by ln of a plus c. All right. So that's just, again, just grabbing prior knowledge and putting it into action. All right. I'm looking for a function whose derivative is sine. Well, I know the derivative of cosine of x is equal to negative sine of x. All right, so I need the antiderivative of just the sine of x. So the derivative of cosine is sine of x times -1. All right, so perhaps if I go in the opposite order, sine's antiderivative would be cosine of x divided by -1, which I could just write as negative cosine of x. So reverse order. And at any point, you test these out by popping them into Desmos. You put in your antiderivative. Let Desmos figure out what its derivative would be. That should give you your integrand. All right. And if you're not sure, then you type in, I mean, if you don't recognize this as being the sine function, then you type in y equals the sine of x to really convince yourself. Oh, I already have the equals. Sine of x. You see, we got a Macharuski here. So we are in great shape. Right? It's the same function. All right. The derivative of sine is equal to cosine. So perhaps the antiderivative of cosine is sine. I'm being theatrical. I mean, if the derivative of sine is cosine, then of course the antiderivative of cosine is sine. Just don't forget the plus c. All right. Tangent's a weird one. Secant's a weird one. Those I actually have to just give you. I'm gonna show you on the calculator in a second. Actually, the next 4 are weird, so I'll come back to those in a minute. But the derivative of tangent, so derivative of tangent, not antiderivative. So we're coming down to this one here. All right. Actually, you know what? I'm gonna save these 4 for next time because they involve quotient rule. So I want to kind of do it right. And I'm looking at the clock. So the derivative of tangent, I'm just going to jot this down here, happens to be secant squared. So the antiderivative of secant squared would be tangent. The derivative of cotangent is negative cosecant squared. All right, so you think of it as negative cosecant squared times -1. So going the other way, I would find the antiderivative of cosecant squared as cotangent of x divided by -1. So negative cotangent of x. The derivative of secant of x is secant x tangent x. So the antiderivative of secant x tangent x would be secant of x. So these are all facts. These are all things that we know. We've used before. In some cases, many times. In other cases, not as many times as I would have liked, but some of them just don't come up very often. Right? But they're all rules that we know, we've used. The thing is, you're always looking them up. You don't have that instant recall. You know, it seems like black magic. It's hocus pocus. All right. The derivative of cosecant of x is negative cosecant x cotangent of x. But again, we could think of that as cosecant of x, cotangent of x times -1. So if I'm going backwards from cosecant x, cotangent x, the antiderivative would be cosecant x divided by -1. All right, so negative cosecant x plus c. You can also think of it as involving constant multiples. You can kind of play around with coefficients and stuff like that, but that's kind of beyond, right? At least beyond today's lesson. I mean, we'll get to that, but not today. The last one, there really is no lesson. I just have to flat out give it to you because this is a rule that you won't know the backstory behind until Calc 2. The antiderivative of the natural log of x is x ln x minus x plus c. I said minus x, but I wrote plus minus c. All right. And that one, the best I can do at this point is just, it's not a proof, but a little bit of a justification. X ln, I mean, I could prove it with the product rule, but it's, again, kind of more of a Calc 2 sort of thing, right? But for now, we just want to know the rule, right? So the original function x ln x minus x plus c should have a derivative of the natural log of x. All right, so just a quick checkarooski here. You can see they're mapping to the same location. So this is a true rule, right? You won't learn the reason behind this one until you get to a topic called integration by parts, one of those techniques that I was talking about earlier. Again, in Calc 2, again being the word of the day, again, A-G-A-I-N, again. But yeah, that's the thing. It's like, like to be continued, you'll have to wait and see, but you'll get there, all right? For now, you're just going to take it on faith. And I can tell you, I mean, I don't know what kind of environment your Calc 2 class is going to have, whether it's going to be in person or remote. But if it is in person, the more of this stuff that you commit to memory, the better off you're going to be, right? Because you knew the honeymoon was going to end at some point. So yeah, you gotta make sure that you have this stuff down because it's that important, right? So commit this stuff to memory as soon as possible. And, in this course you can get away with it, but Calc 2 there will be a reckoning, right? If you don't know this information, right? So start memorizing. I mean, you had to memorize the unit circle at one point, and if you haven't, you better get on that too. But it will get to a point where it'll all catch up to you if it hasn't already, and it won't be pretty, right? So definitely take the time to study this stuff, right? So that's where I'm going to leave it for tonight, because I don't want to tell you to spend a lot of time studying stuff and then not give you the time to do it, or just move on. Oh, okay, now that I told you that, I did my part, and now let's move on to something else. So I'm going to say, let's leave it there. You know what you got to do. You're going to study this stuff. You're going to try to commit as much of it as you can to memory. But next class we'll pick up and continue on. All right. So let me stop the recording.